Hello, students. We are going to start a new chapter today, that is waves. It is somewhat related to the oscillations that we have seen in the previous lectures. In this chapter, we will see about different types of waves, that are transfer and longitudinal waves. Then we'll see the displacement relation for progressive wave. In the oscillation chapter, we have seen the wave that was stationary. Now, in this chapter, we'll see the waves that are progressive. That means they are moving with time. Then we'll see the traveling of wave, the different waves, transverse and longitudinal wave, the equation of speed of sound. Then we'll see the factors on which the speed of sound depends. That is the density of material, the temperature, etc. Then we will represent sound as a pressure wave. Then we'll see the principle of superposition of waves. That means what are the effects when two or more waves are combined at a point. Then we'll see the reflection of waves and the boundary conditions for that. Due to superposition of waves, there will be different effects that are beats, standing waves, and the interference. We'll say standing waves and normal modes, the beats that occurs due to the difference in frequency. Then we will see the Doppler effect, that is the change in frequency due to motion of either object or the listener or both. Then we'll see some basic characteristics of sound, that are intensity, pitch, etc. Then we'll see acoustic of buildings, how buildings are designed, sound absorbing materials, how the roofs should be designed, etc. And at last we'll see the supersonic speeds and shock waves that are created due to motion of jet planes in air. So let us begin. So first of all, let us understand what is wave. Most of us experience the phenomena of wave propagation when we drop a stone in the pond of still water. Whenever we drop a stone, we'll see this kind of pattern created in the pond. These waves move outwards in expanding circles until they reach the shore. It seems as if the water is moving outward from the point of disturbance. If we examine carefully the motion of a leaf floating on a disturbed water, we see that leaf will move up and down about its original position, but there is no displacement of leaf towards the shore. See, the waves are moving towards the shore, but the leaf will be just moving up and down. Thus we can say that energy is transferred, but there is no transfer of medium. Such a pattern in which there is no actual transfer or flow of matter as a whole, but energy is transmitted from one part of medium to another part, is called wave. The waves traveling in a medium are closely connected to harmonic oscillations. This can be easily understood with an example of spring. Consider a group of spring connected. If one end of the spring is pulled suddenly and released, the disturbance travels to its other end. Now, the second spring is also stretched or compressed since it is connected to the first spring. Similarly, the third spring is compressed and so on. Thus, the disturbance moves from one end to other end, but each spring only executes simple harmonic motion about its mean position. So actually, the spring is not traveling, just the energy is traveling through the springs. Similarly, we can consider the propagation of sound waves in air. As the wave propagates, it compresses and expands a small region of air. The density increases in the small region which is compressed, and hence the pressure in that region increases. The pressure is directly proportional to force. Therefore, there is a restoring force acting in this region which is proportional to the disturbance, as in the case of spring. If one region is compressed, the particles of that region are collected together. These particles then tend to move outward in the adjoining region, thus creating compression in the adjoining region. So, we can represent it like this, that at particular point there is compression, the pressure is increased, and due to this in the following region there is a rarefaction and pressure is decreased. Now, in this way, disturbance is propagated through the air in the form of compression and rarefactions. So, this was about the wave. The definition of wave, that is the transfer of energy and not the transfer of actual matter or medium. Now, let us see different types of waves. Basically, waves are classified as mechanical or non-mechanical waves, the electromagnetic waves, and matter waves. So let us see them one by one. The mechanical waves. These are the waves which requires medium to propagate. The best example of mechanical wave is sound wave. Sound wave will require medium to propagate because we know we cannot hear in vacuum because there is no medium, so the transfer of energy cannot take place. So this is the mechanical wave. The other example are water waves, spring waves, etc. The non-mechanical waves are the wave which does not require any medium to propagate. They are electromagnetic waves. So, they are also called the non-mechanical waves. And they do not require any medium to propagate. The best example of electromagnetic wave is a light wave. We can say that it does not require any medium to propagate because it is traveling from sun to earth and there is no medium in between. So we can say that light is electromagnetic wave. The other example are X-rays, radio waves, which are used for communication, etc. The third type is matter waves. The matter waves are associated with constituents of matter such as electrons, protons, neutrons, atoms, and molecules. We can say alpha particle, alpha radiation, beta radiation are the matter waves. In this particular chapter, we will focus more on mechanical waves and especially the sound wave. Now, let us see the types of mechanical wave. The mechanical waves can be transverse wave and longitudinal wave. So let us see one by one what is transverse wave and what is longitudinal wave. In the case of transverse wave, the direction of propagation and the vibration of particle of medium they both are perpendicular to each other. So if wave is propagating in this direction, the particle will be vibrating perpendicular to the direction of propagation. That kind of wave is called transverse wave. So in this case, the vibration of particles is perpendicular to the direction of propagation. Let us see with an example. We have attached one end of a string to a rigid support, and from the other end we will give a pulse. So this pulse will be traveling towards the fixed end. Here the vibration of string particles are perpendicular to the direction of propagation. But if we continue the periodic up and down jerks, then this kind of situation will be created. This disturbance moves from left to right, but the particles of the string oscillate up and down. The particles are not actually moving, they'll just oscillate up and down. So we can say that the particles of rope are oscillating about their mean position in a direction normal to the direction of wave motion. Hence, the transverse wave is created. The second type is the longitudinal wave. The longitudinal waves are the wave in which the constituent particles of medium they will vibrate parallel to the direction of propagation. So, this kind of wave are longitudinal waves. For this, we can take an example. Consider a long air-filled pipe with a piston at one end. Now, if we suddenly move the piston right and then left, then we can generate a pulse of compression and rarefaction. So as we move it right, there will be compression, and compression the pressure will be more, there will be rarefaction, the pressure will be less, again the compression of high density region, again the rarefaction. So in this case, the wave is propagating in this direction and particles are also vibrating parallel to the direction of propagation. So this is the longitudinal wave. The solids have fixed shapes. So solid and string under tension can sustain shearing stress, but fluids do not have fixed shape. Therefore, fluids do not sustain shearing strain. So the propagation of transfer mechanical wave is such that it produces shearing stress in a medium. This is the reason that the transverse wave cannot be propagated through fluids. But the longitudinal wave can propagate through all solid, liquids, and gases. So transverse wave are present in solids only, but the longitudinal wave are present in all solids, liquids, and gases. Just at the beginning of the chapter, we have seen the waves traveling on the surface of water. The motion was the leaf due to the disturbance created in water was up and down. That means if we consider the case of water, then inside the water the longitudinal waves exist, and on the surface of water both longitudinal as well as the transverse wave exist. Now let us see the displacement relation between for the progressive wave. The meaning of progressive wave is that the wave is traveling from one point to another. That means the energy is traveling from one point to another. Let us take an example of a wave. The wave is traveling along x-axis and the vibration of particle is perpendicular to it, that is along y-axis. So this wave can be written as y is equals to, if the amplitude is a, then y is equals to a sine of omega t plus or minus kx plus phi. Here, compared to the equation that we have seen in last chapter, there is a new term, that is kx. This omega is angular frequency, t is time, phi is the initial phase. The term kx will give the direction of propagation. K is called propagation constant and its value is 2 pi by lambda. This x shows that the direction of propagation is along x-axis. Now, it is positive x-axis or negative x-axis. Let us decide that the value, let's say we are taking omega t minus kx, then omega t minus kx will always be constant. Let us differentiate both the side with respect to time. So we can write omega is equals to k dx by dt. Dx by dt is velocity is equals to omega by k. If we had taken omega t minus kx, then this velocity is positive. So if it is given in the equation that omega t minus kx, then for minus kx, the wave is traveling along positive x-axis. And for the plus kx, wave is traveling along negative x-axis. Now let us have the detailed discussion on the equation y is equals to a sine of omega t plus or minus kx plus phi. This omega is the angular frequency and its SI unit is radian per second. K is the propagation constant. That is 2 pi by lambda. Its SI unit is radian per meter. And phi is the phase difference. Now we have seen that V is equals to omega by k. We have just proved that V is equals to omega by k. This V is wave velocity. Or we can say it is the speed of traveling wave. So V can be written as omega, that is 2 pi f, and k can be written as 2 pi by lambda. This 2 pi will get cancelled out. So V will be equal to f lambda. Here f is the frequency and lambda is the wavelength of the traveling wave. Here remember, this V is equals to omega by k is wave velocity, and the equation that we have seen in last lecture, in the previous chapter, that is V is equals to omega under root a square minus x square. This is the particle velocity. For example, we are considering a wave on a stretched string. This wave is traveling in this direction with speed v is equals to omega by k. But different particles on the string will have different velocities, and that velocity is given by this equation: v is equals to omega under root e square minus x square. So this is particle velocity, and v is equals to omega by k is wave velocity. The k, that is 2 pi by lambda, is also called the angular wave number. And 1 by lambda is called wave number. Now, which functions are called wave? It has been analytically shown that any function of space and time which satisfied the equation del square y upon del x square is equals to 1 upon v square del square y by del t square is called or is represent wave. Here y is the wave function and it is not the displacement. If we see y is equals to a sine omega t or y is equals to a sine kx, they individually do not satisfy this equation, so they do not represent a wave. But the functions y is equals to a sine of omega t minus kx, y is equals to a log of at plus bx, y is equals to a sine kx sine omega t, or y is equals to a sine of omega t minus kx plus b cos of omega t plus kx. All this equation will satisfy this condition, so they all represent a wave. Now let us see the equations that represent traveling wave. The equation that satisfy the equation y is equals to, or it is in the form of y is equals to f of at plus or minus bx. It represents the traveling wave or progressive wave. Let us see some examples. Y is equals to a log of at plus bx. Y is equals to under root ax plus bt. Y is equals to ax minus bt whole square. Y is equals to a e power minus b x minus bt whole square. Y is equals to a sine of ax minus bt whole square, etc. They do represent the traveling wave. But y is equals to a sine of, let's say, 2x square minus 3t square. They do not represent the sine wave. There should not be any power of x and t other than 1 in the equation. to represent it as a traveling wave. Now, depending on the source, there are different types of waves. If the source is point source, this is point source, then surrounding it the progressive waves will be spherical. If the source is line source, then surrounding it there will be cylindrical waves. And if the source is plane, then the waves would be plane progressive waves. In our syllabus, we are just asked to recognize the equations of the spherical and cylindrical waves. Here, y is equals to a upon r sine of omega t minus kr. They represent the spherical waves. And y is equals to a upon root r sine of omega t minus kr. They represent cylindrical progressive waves. And the plane progressive waves are represented as a sine of omega t plus or minus kx plus phi. Here, the spherical progressive wave's amplitude depends on the distance, as well as same the case for the cylindrical progressive wave, but for the plane progressive wave, the amplitude is independent of distance. Let us see the different forms of plane progressive wave. First, a basic form, that is y is equals to a sine of omega t plus or minus kx. The other form is a sine of omega can be written as 2 pi by t plus or minus k can be written as 2 pi by lambda. So that will be a sine of 2 pi t by capital T plus x by lambda. But 1 upon time can be written as frequency and 1 upon lambda is written as wave number. So a sine of 2 pi ft plus or minus nu bar x. Here nu bar is the wave number. From the equation we can take k common, so a sine k into omega by kt plus or minus x. That can be written as a sine 2 pi by lambda vt plus or minus x, because omega by k represents the wave velocity. So these are the different forms through which we can represent a plane progressive wave. Now, we should try to understand the mechanism of longitudinal wave motion in terms of compression and rarefaction. The longitudinal wave can also be represented by a transverse displacement position graph. The displacement in this case is, however, being those of the vibrating particles in the line of interval of the wave. So, y and x are in same direction in the wave, but they are at right angles to each other. If we represent a wave, then this point will be of rarefaction, this points will be of compression. Again, at this points there will be compression. So the longitudinal wave can be represented as compressive and rarefaction waves. Now let us see an example. The frequency of tuning fork is 150 Hz. So F is given 150 Hz. And the distance traveled by the sound in air is 20 centimeter in one vibration. So the wavelength is 20 centimeter. We want to find the speed of sound in air. V is given by F lambda, just we have derived. So frequency is 150 into lambda is 20 divided by 100. So the speed will be 30 meter per second. Now let us find the speed of traveling wave. In that case, we will find the speed of wave on different mechanisms. First, let us see the speed of transverse wave on stretched string. The speed of mechanical wave depends on the inertial and elastic properties of medium. And it is inversely related to the inertial property and directly proportional to the elastic property. In case of stretched string, it is proportional. The inertial property is the linear mass density. The linear mass density is mu, that is mass per unit length. We cannot send wave along a string unless the string is under tension. Therefore, we can associate the tension with the elasticity of the string. The speed is derived by the dimensional analysis. Speed on a stretched string is c under root t by mu. Here c is constant. For the exact formula, we'll have c is equals to 1. So v is equals to under root t by mu. This is the speed of transverse wave on stretched string. Here mu is the linear mass density, that is mass per unit length. From this we can see that speed in stretched string is directly proportional to root t. Let us see an example based on this formula. Calculate the velocity of transverse wave in a string which is stretched by a load of 15 kg. The mass of string is 3 into 10 power minus 2 kg and the length is 2 meter. First we will find the linear mass density, that is mass per unit length, that is 1.5 into 10 power minus 2. The velocity is given by under root t by mu. The tension force is 15 due to 15 kg, that is 15 into 10 divided by 15 into 10 power minus 3. So speed will be 10 meter 100 meter per second. Now let us see the speed of longitudinal wave, that is speed of sound. In the longitudinal waves, the constituents of the medium oscillates along the direction of wave propagation. The speed of a longitudinal wave also depends on inertial property as well as the elastic property of the medium. The longitudinal waves, such as sound, travel in the form of compression and rarefaction. Therefore, the bulk modulus of the medium can be associated with the elastic property of a media, because due to compression and rarefaction there will be change in pressure. So we can consider the bulk modulus B as minus of delta P divided by delta V by V. Here delta P is change in pressure, delta V is change in volume, and V is initial volume. Further, the initial property relevant for the propagation of these waves is the mass density of that medium. So, by simple dimensional analysis, we can write speed of sound wave is equals to under root B by rho. This will be the formula of speed of sound through any medium, fluid or solid. But only for solid. Instead of bulk modulus, we will consider the Young's modulus. So speed will be equal to under root Y by rho. Here rho is the mass density of medium. Let us see one example based on this formula. Calculate the speed of longitudinal wave in steel. Given Young's modulus for steel is 3 into 10 power 10 Newton per meter square and the density is 1.2 into 10 power 3 kg per meter cube. The formula of speed of sound is V is equals to Y by rho. That is 12 into 10 power 4 divided by 3 into 10 power 10. The value of Young's modulus is given 3 into 10 power 10 divided by the density 12 into 10 power 4. So the Young's modulus will be, velocity of speed will be 5000 meter per second. Now let us see the speed of sound in gases by Newton's formula. We can easily estimate the speed of sound in gases by the ideal gas approximation. For ideal gas, we can write PV is equals to N kb into T. Here, N is the number of molecules per unit volume. And Kb is the Boltzmann constant. The Newton assumed that when sound waves propagate through gas, the change in pressure and volume of the gas are isothermal. That means the temperature will constant. The amount of heat produced during compression is lost due to surroundings, and the amount of heat lost during rarefaction is gained from the surroundings. So the temperature of the gas will remain constant. So for isothermal compression, we can write P delta V plus V delta P is equals to 0 as temperature is constant. So P is minus delta P divided by minus of delta V by V, and that is equals to bulk modulus. So we have seen the formula V is equals to under root B by rho. So instead of bulk modulus we can write P. So V is equals to under root P by rho. This relation is known as Newton's formula. Let us see an example based on this formula. The speed of sound in air at NTP is 332 meter per second. This is the observed value. We want to find the percentage error in the speed of sound as calculated from the Newton's formula. Given density of air is 1.293 kg per meter cube. The speed of sound is given by under root P by rho. At NTP, the pressure is 1.01 into 10 power 5 Pascal divided by density 1.293. This will give us the answer 280 meter per second. Now, the percentage error will be 332 minus 280 divided by 332 into 100. That will be approximately 15.7%. So, from this we can see that the Newton's equation does not give the correct value of velocity of sound in air. So, we have to do some modification in this. The Laplace gave the modified equation. So, let us see that. Newton assumed that the pressure variations are isothermal. But the Laplace pointed out that pressure variations in the gases when sound propagates are so fast that the heat does not get enough time to flow to surroundings from the surroundings to keep the temperature constant. That means Newton has considered it as a slow process, that is isothermal process, but Laplace has considered it a fast process. A fast process in which heat is not transferred or exchanged is called the adiabatic process. So, for an adiabatic process, we can write PV power gamma is equals to constant. Here, gamma is the ratio of Cp and Cv. From this, we can write P delta V power gamma plus V power gamma delta P is equals to 0. This will be multiplied by gamma. So, gamma P is equals to minus of delta P divided by delta V by V, that is the bulk modulus. So, the speed of sound in air is B by rho, that is bulk modulus upon density, and the bulk modulus is gamma P by rho. This will be the correct formula, and this is Laplace's formula. Let us see an example based on that. Calculate the speed of sound in hydrogen at NTP if density of hydrogen at NTP is 1/16 of air. Given the speed of sound in air is 332 meter per second. The speed of sound in air is given by under root gamma P divided by density of air, and speed of sound in hydrogen is given by under root gamma P upon density of H. For air and hydrogen both, gamma is equals to 1.4. So, taking the ratio, we can write VH by VA is equals to under root density of air upon density of hydrogen. But it is given that density of hydrogen is 1/16 that of density of air. So, rho A divided by rho A by 16, that is equals to root 16. So, velocity of hydrogen is equals to 4 times velocity in air. That will be equal to 4 into 332. So, velocity in hydrogen will be 1328 meter per second. Now, let us see sound as a pressure wave. Since sound waves are detected by the pressure changes which they produce, they are often described in terms of pressure variations. Consider a sound wave whose displacement time equation is given by y is equals to a sine of kx minus omega t. This displacement produced pressure variations which are typically of order of 1 Pascal and so. We can now express a sound wave in terms of pressure fluctuations delta P. For the wave described by this equation, consider a small element in a medium confined within x and x plus dx. In the undescribed in the undisturbed state. The volume of element in the undisturbed state will be V is equals to A dx, where A is the area of cross section. Now, as we have wave propagating through the element, the ends of the elements are displaced. Initially, this end was at this position, it is displaced by y. The another end is also displaced by y. Plus dy. So, the increase in volume of the body or of the element is dV is equals to A dy. The bulk modulus or bulk strain is delta V by V, that is dV by V, that is A dy divided by total volume is A dx, that is dy by dx. Now, change in pressure or excess pressure delta P can be written as minus B delta V by V, that is minus B dV by V minus B dy by dx. Now, our basic equation was y is equals to A sine of kx minus omega t. That can be written as, if we differentiate both their side with respect to x, so dy by dx is equals to A k cos of kx minus omega t. As delta P is equals to minus B dy by dx, it can be written as minus B A k cos kx minus omega t. So this is the pressure variation and it is represented as a wave. The maximum pressure is delta P naught is equals to BAK, and this maximum pressure is called pressure amplitude. We can see from this two equation delta P is equals to minus BAK cos kx minus omega t, and at that time the y was A sine of kx minus omega t. So from this we can conclude that the displacement equation and pressure equation are out of phase by pi by 2, and hence when the displacement is 0, pressure is maximum and vice versa.